A spinning object rotates about its center of mass. In physics, we consider two types of motion, translational motion and rotational motion. Translational motion means an object starts in one place and moves to a different place. It doesn't necessarily have to be done in a straight line, but translational motion means an object starts one place and ends up somewhere else. In translational motion, the object's entire mass can be assumed to be at its center of mass. And so when we study translational motion, we often consider the object to be a so-called point mass. In rotational motion, of course, what we're talking about is some sort of spinning or circular motion. In rotational motion, the object is usually considered to be an extended mass because the rotation is crucial to the motion. So in a boomerang, if we're studying all the aspects of its motion, we have to take into account its rotational aspects, so we could consider the boomerang to be an extended. In translational motion, an object's resistance to changing its state of motion is its inertia. The greater the mass of an object, like the Titanic, the greater the inertia. The smaller the mass of an object, the smaller the inertia. In rotational motion, an object's resistance to changing its state of motion is called its moment of inertia, symbolized by capital letter I. It's also called the rotational inertia, and the key idea with the moment of inertia is that the more mass that's farther from the axis of rotation, the greater the moment of inertia. So, when an object is rotating, it can be rotated about several different points. The baton twirler, for example, if he holds the baton at the center, there is a certain amount of mass of the baton that is a certain distance from the center. If he holds it at the end, there's more mass of the baton that's farther from the rotational axis. And for that reason, a baton that's held at the end has a greater moment of inertia than one that's held at the center, which means that it's not only tougher to get that baton started rotating if we're holding it at the end, but it's also tougher to stop it from rotating once it already is. This is why baseball players, you can see Babe Ruth in the lower left here, hold the bat at the end, because there's quite a bit of mass of the bat that is quite far from the axis of rotation, which is at the hands of the batter. It's more difficult to get that bat rotating when it's held at the end, but it's also tougher to stop it from rotating once it already is rotating. And that's what batters want, because that will impart a greater force to the ball. Sometimes when batters have two strikes, they will choke up, which means they will put their hands closer to the center of mass of the bat. It's much easier to get the bat rotating when you do that, but you also don't impart nearly as much force to the ball because of that change in the moment of inertia. Moment of inertia formulas have been compiled for simple shapes. That formula, 2/5 mr squared, is the moment of inertia for a solid sphere spinning about its central axis. The Earth, for example, is approximately a solid sphere spinning about its central axis. And there are many other shapes and configurations for which moment of inertia formulas have been compiled. For a point mass that's revolving at radius r, the moment of inertia equation is mr squared. For a basketball, for example, that's spinning on someone's finger, the moment of inertia is 2/3 mr squared. And there are many, many formulas that have been compiled. I've just given a couple of examples here. Now, what are the SI units for moment of inertia. The SI unit for inertia is the kilogram, right? Because inertia is related to mass. Well, for the moment of inertia, we talked about that the moment of inertia depends on how much mass and how far away from the rotational axis. And you can see here from these equations that they all have in common mr squared. So m is mass, r is a distance, so the SI unit for moment of inertia is typically the kilogram meter squared. Let's summarize. A rotating object spins about its center of mass. Translational motion is here to there motion. We often treat objects as point masses when we model translational motion. Rotational motion involves circular motion or spinning. We often treat objects as extended masses when we model rotational motion. The moment of inertia is an object's resistance to changing its state of rotation. Its value is related to an object's mass and geometry, and its SI unit is the kilogram meter squared.